Okay guys, so welcome back again to another video. So today we are going to talk about the metal alkene complexes, or we commonly call as olefins, right? Okay, so let's move on. So let's see, we have our metal center. Let me take another call. Let's take let's say we have our metal center like this. Okay, so now alkene, right? This is alkene. So you know what alkene is, right? Let's take the simplest alkene like this. Okay, now how this alkene is going to bind with our metal center? You know, like most of the ligands, right? Most of the ligand, when we form in the metal ligand bond, the first step is the sigma donation, right? First step is the sigma donation. But in this case, right, there will be no sigma donation. This 5 electron cloud here, this 5 electron cloud will be the key factor which is contributing to our metal center. This electron density will be the one which will be donated to our metal center. So the best orientation, you need to understand this, best orientation to bind with our metal center is like this. Here we have hydrogen, here we have hydrogen. Now here we have our 5 electron cloud. It will be donates its electron density towards our metal center. So this is our first step when the metal center is bind to a alkene complex. Okay, now this is our first step. I have told you this is our first step. The second step can be the back bonding, right? Second step can be the back bonding. Now after metal center is formed, you know there are dxy, like T2g orbitals. There are T2g orbital of the metal center. Here we have T2g orbitals of our metal center. Now the bond is formed between our carbon like this one, and there is a particular p orbitals on our alkene like this. So let me take with the perfect alignment. So let's say like this, our p orbitals on our carbon atoms in our alkene, if these orbitals are perfectly aligned, perfectly symmetrically aligned with our T2g orbital, one of the T2g orbitals in our metal center, then there can be back bonding. Here the back bonding will be formed, right? Here the back bonding will be formed. So this is the orientation of our metal alkene complex. So first thing what happens is our 5 electron cloud will be donating its electron towards our metal center. Then if there are conditions, if there are perfect condition to occur back bonding, then there will be T2g orbitals and the pi orbitals of our carbon will be combined together to form the back bonding effect. So when the back bonding is happen, there are some changes in our orientation. So here we have our metal center and it is directly connected to our alkene. So this is when there are no back bonding. Right? This is when there are no back bonding. Now look at this. When the back bonding is happening, right? So let me take the red color. Okay. Now back bonding is happening. You can see there will be a bond forming with our metal center with this carbon, and another bond is forming with metal center and this carbon. So the back bond, when the back bonding is at its maximum, when the back bonding is at 100%, our bond will be changed like this. This is back bonding at its maximum effect, 100%. This is the back bonding when it's at maximum position. So you need to have a good idea about this thing. Now the most questions is about this bond length, right? This bond length. Look at this. Now this is no, in this case there are no back bonding, right? In this case there is a back bonding. So when there are no back bonding between the metal center and our alkene, right, you can see there is a double bond character between the two carbons, right? There's the double bond character between the two carbons. But when the back bonding is happening, right, when the back bonding is at maximum, you can see between the two carbon there will be no double bond character, just the single bond character. So mostly this carbon is now sp3, this carbon in here is sp2. So what will happen to the bond length, right, between the two carbons when the back bonding and at its maximus, when the back bonding is happening, the carbons are sp3, which resulting the length between the two carbons increased. In this case, when no back bonding is happening, double bond character will be there between the two carbon, or we can say the carbon is at sp2 hybridization, so the bond length is decreased. These are the important factors when you are answering the questions, right? When you are answering the questions, like do not just write the answer like because of the single bond this character is long, because of the double bond this is short. Like the most convenient answer may be like, due to the back bonding this carbon changes its hybridization to sp3, but in this case this carbon stays in the sp2. That's a more convenient answer. So just try to put your answer based on the scientific manner, right? It will attract you more marks. Okay, now this is the main thing you need to understand. Now we will see what effects, right, what effects can cause to this back bonding phenomenon. Okay, I will take a new one. Okay, now let's talk about the factors affecting back bonding. So we are talking about the olefin, like basically about the olefins, but these can be applied to other ligands too. The first thing is, here we can say, now here we have a metal center, right? Here we have the metal center. Now let's say we have CH2 double bonded CH2. You know, now the first step in this case, the 5 electron cloud has to donate its electron density towards our metal center, right? When this happens, our metal center's electron density will be increased. So this increased electron density will result in our metal centers to get unstabilized. To stabilize the metal center, it will do the back bonding. That's the basic idea about how the back bonding happens. Now to do that, to have a very efficient back bonding phenomena, our metal center must have higher electron density, right? Our metal center must have higher electron density. So the first thing which you need is higher electron density. High electron density on the metal center. Or in other way, if I say the same thing in other words, the metal center should be in low oxidation state. Right? Metal center should be in low oxidation state. Like if I take an example, it's like this. Let's take manganese, right? If manganese at plus oxidation state, and again we say manganese at plus 4 oxidation state, just a hypothesis, right? This is not right. There are no Mn plus 4, but just a hypothesis. So between these two, right? Between these two, which metal center contains the higher electron density? Definitely this one, right? Because you know the plus means the electron positivity, right? Which means it needs electron. But in order to have the back bonding phenomena, the metal center should contain electron, because metal center is the one who's contributing to the back bonding. it is the factor which is donating electron to the ligands. If our metal center doesn't have enough electrons to contribute, it won't do the back bonding thing. So metal center should be in low oxidation state, not high oxidation state. It should contain low oxidation state, right? If your complex is negatively charged, like this one, just an example, right? Just like this one, there's a negative charge, which means your complex or your metal center has high electron density, which is very good for the back bonding. So you need to have a good idea about that. Okay, so let's move on. The next factor which is affecting the back bonding between the metal center and its ligand are the steric effects. So number 2, steric effects. I think you know how that happens, right? If your alkene have so many R groups, so many electronegative groups, like, right, let's say we have Cl2 instead of hydrogens, then okay, I will take this example like this. Let's compare these two complexes, this one and this. This is the hypothesis, right? Just the hypothetical. This is not real. I mean, I just want to explain the theory. Okay, now in this case, you can see like chlorine. Oh, we can take bromine also, right? So when this happens, you can see. Let's take bromine. It's better, I guess. This is bromine. Okay, let me erase it again for me. Sorry about the mistake. If we take bromine, it's much easier you to understand it. Okay, now look at this. Now when in this case our metal center can easily donate its electron towards the vacant p orbital in the carbon, but in this case it's really hard, right? Because there is a bromine atoms. You know, bromine is a very huge molecule and it contains very large electron cloud. So our metal center has so much difficulty to donate electron from this repulsion which generates from the bromine. Bromine has a very huge electron cloud. It will repulse the incoming electron density from our metal center. So these are the steric effects, right? So based on the steric effects, the back bonding can be maybe deteriorated, maybe decreased, or maybe increased. Okay, so let's move on. Let me erase this. And the other main thing is electron acceptor strength. Electron acceptor strength. Or in normal ligands we call as phi acceptancy. Like we have talked about in our previous video. Like if I take two ligands, let's say carbon nitrogen R and carbon monoxides, right? So in this case the carbon has, in this carbon, right, in carbon monoxide, carbon has higher electron acceptancy than this carbon. Why? Because there is an oxygen over here. Oxygen will pull out the electron density from the carbon, which make the carbon electropositive. So there is a obvious way where our metal center can donate its electron towards the carbon, because there is an electron positive character in our carbon. But in this case, look at this, our nitrogen is not much that strong on pulling electron density from the carbon, because the electron negativity is relatively lower compared to oxygen in nitrogen, right? Nitrogen has lower electron negativity compared to oxygen. So nitrogen has relatively lower capability of pulling electron from our carbon, which makes the carbon not that much electropositive. So it's a little bit hard to push or contributing electron density towards the carbon because there is electron density around the carbon. In this case, there are very less electron density around the carbon because all the electron density have been pulled away by the oxygen. But in this case, the nitrogen couldn't do it. This is the electron acceptance strength. In this case, this carbon monoxide have higher electron acceptance strength. This isopropanol group has a lower electron acceptance strength. These are the main factors which affecting the back bonding. You need to have a very good understanding about it. Most of the question will be about like explain this, explain that. So when you are explaining these things, these key points must be there in your answer. So in the next video, we will talk about more examples and questions about how the back bonding can be determined, how back bonding is varied around many ligands.